Hello everyone, my name is Muhammad Tahir Abbas and I'm a PhD student at Department of Computer Science, Karlsruhe University, Sweden. Currently, I'm working on energy efficiency for NB-IoT devices, and which is the topic for my presentation as well. So in this presentation, I'm going to discuss and provide some basic guidelines for an energy efficient tuning of the NB-IoT stack. Here is the outline for my presentation. I will start with the introduction, followed by NB-IoT application. Then I will discuss the energy saving mechanisms for the NB-IoT devices. After that, I will formulate a research question followed by our simulation environment and our methodology. At the end, I will show the results with some final remarks, and then we will conclude this presentation with a question and answer session. Starting with the NB-IoT. NB-IoT stands for Narrowband Internet of Things. It's a new technology proposed by 3GPP with some functionalities inherited from LTE. But we have some additional requirements in NB-IoT. The purpose of NB-IoT is to serve applications generating infrequent data without strict latency requirements. Particularly, the requirement of NB-IoT is to provide deep penetration for both indoor and outdoor coverage. It supports 150,000 connections per cell. The deployment of NB-IoT can be done in both in-band and guard-band of LTE cell. It provides secure and reliable connection. NB-IoT devices comes at very low cost, and most importantly, NB-IoT is optimized for low power consumption with a battery life of 10 years. This is because with the mass deployment of these devices at remote areas, replacing batteries would not only be cumbersome, but also excessively costly. So battery lifetime is a key concern for this technology. So in this presentation, we will investigate the ways to achieve this target. Now coming towards the NB-IoT applications. NB-IoT provides supports for a number of applications, starting with smart metering. It supports water metering and electricity metering applications. It has applications in agriculture and can also be used for vehicle tracking. It supports smart wearables for health monitoring, and it makes buildings even more smarter. Last but not least, smart cities with smart parking is one of common example of narrowband Internet of Things. Okay, in this slide, we will discuss the energy saving mechanisms for NB-IoT devices. When a device wakes up for the first time to transmit a data towards the application server, the radio resource control protocol changes its state, and it makes a transition into RRC connected state after performing a radio connection establishment procedure. So this figure, it shows the energy consumption for a NB-IoT device during different RRC states. The RRC protocol has two states. One is the RRC connected state at the top left corner of this figure, and the other one is the RRC idle state, which is represented on the top right corner of this figure. In RRC connected state, the high blue peaks, they represents the energy consumed during the connection establishment and data transmission, and the low peaks, they shows the energy consumed during the DRX cycles, during which the device listens for any downlink information. At this point, the device alternates between listening and idle periods to save energy. The connected state is governed by a timer named as an activity timer, and that timer is controlled by node B. After this timer expires, the device makes a transition into the idle state, where it is not connected with the network anymore, but still it can listen to the pagings. However, these listening periods are less frequent if we compare it to the connected state to save more energy. And we call these listening periods extended discontinuous reception modes, or EDRX cycles. This period is governed by the active timer, as you can see, timer T3324. Once this timer expires, the device moves into the power saving mode to save more energy, where it turns off its radio and goes into the deep sleep mode. Lastly, the red line at the bottom shows the base energy consumption for the device to keep itself alive. So from the previous slide, we have seen different RRC states with multiple timers, for example, inactivity timer, active timer, or ADRX cycles. So, and we can set them with different values. However, we still have to find optimal values for these parameters so that the battery life can be extended to a period of 10 years while it still fulfills the application requirements of NB-IoT. Now, in order to study the energy consumption of NB-IoT devices, we have developed an NB-IoT simulation environment in OmNet++ framework. Our simulation environment models NB-IoT release 13, and it supports the NB-IoT protocol stack, which you can see in this figure. The blue strip patterns, they actually have been completely implemented as specified by 3GPP. And the wavy pattern layers have been partially implemented with those parts which are essentially to properly model the energy consumption of an NB-IoT device. Finally, the white colored layers are only implemented in our simulation environment to the extent that they are able to properly communicate with the adjacent upper and lower layers. I also would like to mention that CoAP layer has support for reliable transfer with confirmable messages being retransmitted using a default timeout. Now coming towards our methodology, we have divided our simulations into two groups. The first group, it supports full DRX support, where we have DRX during the connected state and the idle state. Partial DRX support, where we have DRX enabled only in the idle mode state. And for these groups, we have performed experiments for different traffic densities, traffic burstiness, and different RRC inactivity and active timers. For these experiments, initially, we have set the inactivity timer to 20 seconds, active timer to 30 seconds, DRX cycles, they are set to 1.28 seconds, and the hard block error rate is set to 10%. During our experiments, we kept all these values unchanged. So we will start with the full DRX support. This graph, this shows the energy consumption for a period of 10 years for different traffic densities. In this experiment, we have sent a single message after every 3, 4, and 5 hours over a period of 10 years. Y-axis shows the total energy consumed, and x-axis shows different random access delays. I would like to mention that these delays actually represent the time required by a device to access physical resources in order to set up a complete radio connection. The red line shows the target energy consumption which we want to achieve, and the green line, it shows the total energy consumed by the device while staying in the PSM state for a period of 10 years. From the figure, we can say that the energy consumption increases with an increase in random access delays along the group of bars, and it also increases with different traffic intensities. So we can say that a less dense traffic, which we can see in the white and blue bars, where we are able to achieve a battery life of 10 years for the first and second group of bars. So from this figure, we can say that a more dense traffic results in more energy consumption, and a quick radio connection reduces the energy consumption. So now coming towards the traffic burstiness. In this slide, we are sending messages in bursts. We are sending the same number of messages in a burst of 1, 2, and 4. The graph on the left, it shows the energy consumption for different bursts of traffic, which increases along a group of bars due to the increase in random access delays. And it decreases drastically within a group of bars due to the increase in burst size. However, the graph on the right, it shows the number of RRC connections for the same experiment. And we can observe the decrease in RRC connection within a group of bars. So from this figure, we can say that sending messages in burst is efficient, and which reduces the number of RRC connections. And number of RRC connections, they impacts the energy consumption directly. Now in this slide, we will see the impact of different inactivity and active timers over the energy consumption. The graph on the left shows the energy consumed for 5 different inactivity timers, which we can see on the y-axis, and we can see the different random access delays on the x-axis. So from the graph, we can say that a very short inactivity timer of 0 seconds has a huge impact over the energy consumption. This is because the radio releases its connection immediately and moves into the RRC idle state. However, it needs to set up a new radio connection again to receive the acknowledgement back from the application server after listening to the pagings during the EDRX cycles, which actually results in an extra energy consumption. However, the graph on the right, it shows the energy consumption for different active timers. And we can see that changing active timers from 60 to 30 seconds, it marginally impacts energy. And this energy efficiency comes from the EDRX cycles during the active timer. So from this figure, we can say that a very short inactivity timer is crucial, and active timer shows almost no impact due to the EDRX cycles. Now coming towards this slide, this graph shows the impact of QAP retransmissions. QAP performs a retransmission of the same data again if we don't have any acknowledgement back before QAP retransmission timer expires. Here we have set the QAP retransmission timer to different values of 2 seconds, 4 seconds, and 8 seconds. And we have also increased the round trip time to 8 seconds in order to observe the impact of it. So in this figure, you can see the energy consumed for different QAP timers on the y-axis and different inactivity timer on the x-axis. From the figure, we can say that a long inactivity timer with a large QAP value saves more energy. This is because a very short inactivity timer forces the radio to go into the idle state, and a very short QAP value forces a new radio connection. So from this, we can say that QAP with a short value results in extra QAP retransmission and a new RRC connection setup. And QAP retransmission is expensive if it happens after the inactivity timer expires. Now coming towards the partial DRX support results. So in this slide, we will see the impact of inactivity and active timers over the energy consumption when CDRX is disabled. The graph on the left, it shows the energy consumed for the 5 different inactivity timers, which we can see on the y-axis. We can see different random access delays on the x-axis as well. So from the graph, we can easily observe that a very short and a very long inactivity timer has a huge impact over the energy consumption. This is because in a case of a short inactivity timer, the radio releases its connection immediately and moves into the RRC idle state. However, it needs to set up a new radio connection again to receive the acknowledgement back from the application server. However, in the opposite case, where we set the inactivity timer to a very high value, keeping the radio active continuously is very expensive. Now, coming towards the graph on the right, the graph shows energy consumption for different active timers, and we can see that changing the active timer from 30 seconds to 60 seconds marginally impacts the energy. And again, this energy efficiency comes from the EDRX cycles. So from this figure, we can say that increased energy consumption with an increase in activity timer. The impact of active timer on the energy consumption only marginally increases with the increasing EDRX cycles. Now, this graph shows the impact of QAP retransmissions. In this figure, you can see the energy consumed for different QAP timers on y-axis and different inactivity timers on x-axis. And from the figure, we can say that inactivity timer of 5 seconds with a QAP of 8 seconds, it saves more energy and is a optimal solution here. So from this figure, we can say that QAP with a short value results in extra QAP retransmission and a new RRC connection setup. And QAP retransmission is expensive if it happens after the inactivity timer expires. Finally, here is a summary of this presentation. We have seen in the previous slides that traffic density impacts the energy consumption directly. So a less dense traffic with burst is efficient. Keeping the inactivity timer slightly longer with the support of CDRX, and keeping it a bit shorter when CDRX is disabled is efficient. Finally, the co-app retransmission should always be set to a value which is higher than total round trip time to save RRC connections and hence the energy as well. Now, our future work involves working on the NB-IoT devices in order to perform some real-world measurements to see the impact of different parameters over the energy consumption. Thank you all for your time.